So let's deal now with what is called the strength or the reactive strength index. And this is perhaps a slightly misleading term because the word strength is in here and it's been referred to previously on one of the other slides. But what is the reactive strength index and kind of what is it in terms of its mode and its function? Well, as we've already talked about, researchers and practitioners previously measured things like squat jumps and counter movement jump heights, and they've done that kind of independently, and they've looked at the difference between the two jumps. And they've looked at those, looking at things like pre-stretch components of the counter movement jump. And what it's been argued that there's an absence, right, of any preloading. And so the net result is that the squat and the counter movement jumps don't provide an adequate representation of the stretch shortening cycle. Remember that fundamentally, all they really reflect is fundamentally that concentric phase. The only way that you get the eccentric phase and therefore get the full stretch shortening cycle is by having the muscle under stretch, having the muscle under braking forces. And this is where the reactive strength index comes in. And the reactive strength index, we've kind of looked at it already, is really taking a drop jump and perhaps just finessing that data a little bit to make it easier to understand what we're working with. And it's this tool that's used to examine the interaction of the jump height, that's in the concentric phase, and the contact time. So in other words, it's notion, S&C coaches refer to this as kind of rebound capability. But in other words, it comes back to what we've been referring to all along within this session, which is that we're dealing with power, so it's the amount of force, well actually jump height. The higher I jump, the more force that must have been used to jump there, but how quickly I'm getting from eccentric to concentric. So in other words, it's height as a function of time. So the measure is derived from dividing the height jumped, which we've already seen this in terms of millimeters or centimeters, by the time spent in contact with the ground. And what that does, it develops forces to perform the jump and provides an insight then, as I've got here, into the strain experienced by the musculotendinous units. In other words, it's the stretch shortening cycle. If you simply just have the drop jump, so we're going to go back a couple of slides to help us explain this. If we simply just have jump height, that really just tells us, as it is, the kind of more of the how high they jump. It doesn't really tell us anything. If you simply have the contact time on its own, that doesn't really tell us the amount of force that's being produced. But if you divide one by the other, remember we noticed how suddenly how important this data started to become. This is reactive strength index. So it's taking the standard drop jump and in essence giving it a proper interpretation and a correct interpretation. And you can see the ramifications of this in this data set here. So here we've got our graph, we've got our drop height on our x-axis, and then what we've got here is our contact time on our y-axis. And you can see that as the drop height increases, you can see that there is kind of a gradual increase, in contact time here, but then suddenly a massive increase in contact time. But look at the subsequent effect here on jump height. It's exactly as we saw in that example previously. Despite the fact that contact time has got longer, jump height still goes up because it's not had a big enough effect in terms of losing that potential energy. It's only when we start to get from this jump height here, which is about 40 centimeters, and we move to 60 centimeters, we start to see a decrease in jump height. And then when we move from 60 all the way up to, in this case, I think it's about 75 centimeters, an enormous drop off in jump height. So how does that work? Well, if we now divide jump height by contact time, you see this effect here. You can see that the reactive strength index increases to a jump height of 60 centimeters, then we get this sudden drop off. So this now enables the S&C coach to say, well, actually, this would be the optimal drop height to work somebody at. But it also tells us about the range over which they can work. In other words, fundamentally, it starts to tell us where we need to focus in our athlete. Is it I need to focus more on contact time, or is it I need to focus more maybe on the kind of, in inverted commas, the strength component of the action. And so if we look at this data set here, we've got ground contact time on this graph here, and then we've got drop height on reactive strength index, sorry, against drop height on this graph here. And so you can see as the contact time starts to get longer and longer and longer, you start to see the RSI starts to decrease. So in other words, this is the kind of, in this example here, here's the optimal RSI. Remember, it's height divided by time. This is the optimal RSI here. So you can start to see it decrease. That's a natural decrease. You see that in every person. You cannot keep producing high reactive strength index scores as drop heights increase. But people who have got better reactive strength capability, better stretch shortening capabilities, will be able to sustain the RSI over greater drop heights, either as a function of having just better contact times or better power generation in the muscle, or as we would probably expect, it's the combination of the two. Now, in this data set here, we've got the left panel is the mean and the range for reactive strength index across 3 trials, 4 different drop heights, and the right panel just simply shows the mean and the range of the jump height. Now, if we take the RSI, what you can see here is we've got 20, 30, 40, and 60 centimeters. And as we alluded to previously, you can see there is pretty good repeatability in all of these examples. Okay, you can see that both by the mean value, but the spread of the data in all of these, they are pretty much consistent. There's a little bit more variability, oddly, at 30 centimeters than there is at 60 centimeters. But it does tell us that it is repeatable. If we can combine all our learning, we make sure that we've got hands on hips, so that reduces variability in the data. We make sure that there is sufficient recovery time between each jump. We have to do repeat jumps because we've got to make sure that we've got reliable scores. But there has to be sufficient recovery time between each jump to reduce the impact of the neuromuscular fatigue on subsequent trials. So this becomes really important understanding that these tests are both valid and reliable. We know the validity is there because the EMG data showed us that. We can see that they can be reliable if we control arm swing, if we control recovery time, if we ensure that we do this over a sufficient range of drop heights. And you can see this again being reinforced here. So here we've got counter movement power, and then we've got power just in watts, and the same on this panel as well. And what you can see is we've got different drop heights, so 20, 40, and 60 centimeters. And this is max power and this is mean power, okay? But the difference here is G1 to G5. And so G1 is contacts of minimal time and G5 are contacts of the longest time. And what is quite interesting is, look at the mid-range data. So the mid-range is G3. So why is that important? Because the other two are at the extremes. You've gone for minimal contact time or maximal contact time. And what you can see is that kind of mid-range is where they're producing both the highest in terms of the max and the highest average in terms of the power being produced. So we're not producing the highest when we're going for quickest or longest contact times, irrespective of the drop height. You see that at 20, 40, and 60 centimeters in both examples. So again, reinforcing that instruction goes to the heart of the validity of they have to do this in terms of trying to maximize both contact time and jump height.